All right, the recording is live. The mic is working. Before we get into today's topic, we have a couple of things to discuss via housekeeping. Number one is tomorrow's lab, and number two is next week's exam. First, I can talk about tomorrow's lab. Tomorrow's lab is not a wet lab, it is a dry lab, which means I'm a little bit more flexible on clothing and attire. That being said, no food or drink is allowed in the lab, regardless of the type of lab we're doing. So tomorrow's lab for both the morning and the afternoon lab is a dry lab, which means that we'll be going through a worksheet together. I'm flexible on clothing since we're not working with chemicals. That being said, no food or drink is allowed in the lab. Tomorrow's lab workshop will be directly based off of today's material. You probably remember that oftentimes I'll come to class with handouts and worksheets. None of that today because we're doing today's workshop tomorrow during lab. Tomorrow's lab also serves as sort of as a open office hours or review for the exam on Tuesday. I don't have a practice exam for us to go through together, but rather I'll be, of course, there at lab in person, able to answer any and all questions related to the exam. So again, just for tomorrow's lab, it's a dry lab, which means I'm flexible on attire. I will print the worksheet. I will carry it to the lab. You'll have some questions assigned, some we will do together, and of course, some will be extra credit. Tomorrow's worksheet is directly based off of today's content. That's why we don't have an in-class problem set for today. Today is just content delivery, and it may just end up being a fairly short lecture. Do we have any questions about the lab? All right, big one up next, the exam. Our first module exam is next Tuesday on the 16th. It'll be held on our normal lecture time and lecture room. So in here, 11:30 to 12:50. Please show up early. Late students will not be given extra time. The exam will end at 12:50 regardless. And we cover lectures 1, 2, 3, 4, and 5. That includes today. There is a lecture 0 on Canvas. Lecture 0 was the syllabus overview and the course expectations. Of course, that's nothing to be tested on. Now, for the exam itself, like I said, late students will not be getting extra time. I also don't allow makeup exams. So if for whatever reason you cannot come to the exam, that's okay. That's why I do have that dropped exam policy. So if you don't take the exam, you'll be given a 0 for that day. And of course, presumably that will be your lowest score and hence dropped for the course of the semester. As with my exams, there is an extra credit opportunity. We've been building that throughout the course with the in-class problem sets with tomorrow's worksheets. These extra credit opportunities are due Monday night, 11:59 p.m. via Canvas. As you continue to work and practice on these questions, feel free to hit me up or send me a message on Discord. I'm more than happy to check your work. Discord is the fastest way to get back for me to get you a response. Canvas is the slowest response time. There will be an extra credit opportunity on the exam itself. So if you're keeping track, that's 5 points from the assignments and then 5 points on the exam itself. So you can get up to 10 points extra credit, which will really help some scores. All right. No Scantron needed. Any multiple choice questions on the exam, I will give you space to fill in on the exam. So you do not need to carry a Scantron or purchase one. That leads me to say that the only thing you will be bringing to the exam room is your writing utensil, be it a pen or a pencil, your calculator, and that's it. A periodic table will be provided as part of the exam booklet, so you will not be allowed to carry yours in. There will be no cheat sheets, no handouts or references. Everything you need will be on the exam. This is a very good opportunity for me to say, just because I saw your flashcards, you mind if I just borrow the 2 of them? That's because I happen to see yours. If you guys remember the polyatomic ions, I gave you a handout a few days ago, like a week or so ago. You are expected to memorize those names and those formulae. Those will not be provided to you as part of the exam. We have one student here already using flashcards to study them. I recommend that. That's a good idea. All right, but I want you all to understand exactly what to expect the day of the exam, right? There'll be a lot of expectations on you vis-a-vis actually conducting yourself appropriately. I don't condone cheating or plagiarism. Any such cases will be reported to the relevant department and a report will be filed, and I would hate to have to do that. If you are a DSPS student, meaning if you have accommodations, it is your responsibility to request proctoring via DSPS. If you do not request proctoring via DSPS, I will assume you're taking the exam with the rest of the class without your accommodations. So I'll repeat that again. If you have DSPS accommodations, it is your responsibility to request test proctoring from the DSPS office, right? When you do that, I will get an exam. I will get an email saying a student has requested accommodations. I will send them the exam and you're done. If you do not fill this form out, you will not be given extra time under the normal circumstances. All right. So if you're at all confused about what your DSPS accommodations are, how that works, just come talk to me after class. I'm more than happy to clarify some things about that. Don't worry if you didn't grab all of this information down right now. An announcement will be sent out later today that has all of this information. You can see it says will not be visible until 4:30 p.m. today. It has all of the information as well as a specific link for DSPS students to submit that test proctoring form right here. I just have a thing right here. If you are feeling unwell or showing any symptoms related to COVID-19, contact me ASAP. I do have contingencies for those who test positive. If you do not have a positive test result, do not assume arrangements will be made for you. I also break down the specific extra credit opportunities that were allowed and were expected of you, detailing exactly which topics you need to submit. There are 5 in total. This topic right here, atoms, molecules, and ions, we had no problem set. We had no worksheet. So there's no extra credit opportunity for that. But we do have extra credit opportunities for the rest of the subjects. As of right now, the only one we have left is the electronic structure of atoms. That's a topic we're going to do today. And tomorrow's workshop will have some of the extra credit opportunities. When it comes to practicing for the exam, of course, you'll have those question banks that you can refer to. However, on modules, so this is a student view, under modules, under exam, I've posted last semester's Chem 300 exam, as well as the key to last semester's exam. I do recommend you use the practice exam in your studying. This, in addition to my question bank, is what I use to make my exam. So this exam will give you a really good idea of how I test, the way I test, and the types of questions you can expect. Having it load right here. There's some extra credit. There's some true and false, some multiple choice, some nomenclature, fill in the blanks, and a little bit of questions on the periodic table. If you remember, we did a question just like this on the day of the periodic table. And some worked problems that can either take the form of math or today's topic specifically. Do we have any questions about the exam? Like I said, a Canvas announcement will go out with all of this information once again. So if you didn't grab it all right now, that's okay. The one thing I do absolutely want to make clear is during the exam, you're only allowed to have your writing utensil, your pen and pencil, and your calculator. You should not have anything else with you, no handouts or cheat sheets. A blank hard copy of the periodic table will be provided as part of the exam booklet. Let me see if I have that on this one. Yeah, so it'll look like this, where part of the document itself is the periodic table. This was last semester's periodic table. You guys have that nice new colored version. That colored version is what you're going to expect. And of course, if you forget information about the extra credit, there is an assignment for the extra credit to turn in that again goes over details as to what the extra credit is, what topics are expected, so how many submissions you should have. But the one thing it does not have is which questions are the extra credit. If you remember, I assigned those during class. So if you've missed what questions were assigned as extra credit, I do expect you to communicate that with your classmates. Okay. Last chance for any questions related to the exam or tomorrow's lab. Yeah. Regular calculators are allowed. I do not have backup or spare calculators. So unfortunately, if you don't have, I do recommend making sure yours is fully charged and ready to work. Any other questions? Nope. Okay. Let's get into it. You're in my spot. Sorry, my bag wasn't there today. It was at the front. That's my handout. This is instructor notes. Yeah, no handout for today. Where are we? Where are we? Where are we? Okay. Today, on our last topic before the exam, we will be talking about the electronic structure of atoms. Now, when we talk about the electronic structure of atoms, the one thing I really want you to remember, or at least keep in mind, is that we're really talking about the address. Just as we have address for various buildings and the like, electrons and their atoms also have an address. So I'm just going to take an example right here. Let me see what is the exact address of the Elk Grove Center. Okay. So the address of the Elk Grove Center, I'll have it right here. It's 151 Bighorn Boulevard, Elk Grove, California, 95757. Now, obviously, in some way, shape, or form, all of us understand the basic idea of an address. From the right-hand side, we start with the zip code, of course. The zip code is an incredibly large amount of area, but it's specific within the state that we're in. What I'm trying to say here is that over here on the right, we have a wide open address, meaning multiple buildings, multiple places can have or be in California, be at that zip code. As we go even further to the left, the scope narrows. Instead of saying California as a whole, we're saying specifically Elk Grove. Yes, still there are a lot of places that are in Elk Grove that have the address Elk Grove, but we're getting a little bit more specific. Going even further, now we're on the specific street, Bighorn Boulevard. There are many buildings on the street, the school, the high school across the street. There's some construction going on. And I think the fire station just down the road is also on Bighorn Boulevard. But then finally, we get to the most specific part of the address, which is, of course, the building number or the number on the street itself. The idea I'm trying to get you to understand here is that we use a complete address, a complete street address, to understand exactly where something or someone is located. There are different pieces to the address, building number, state, zip code, all that stuff that all tell us various things, but together they give us an exact address for a building. In the same way, electrons have an address. Over the next few minutes, just like there is a zip code, a state, a city, and a street, we're going to see the different ways or different terminologies used to give electrons an address. We're going to draw a table of 4 columns. The first column will be labeled quantum number. Second column will be labeled symbol. Third column is labeled allowed values. And the fourth column, the widest column, is where we'll write the physical meaning, the description of what exactly that means. We're going to go over 4 different quantum numbers, not necessarily evenly spaced rows, but we're going to go over 4 of them. The first one is known as the principal quantum number. The principal quantum number has the symbol N as in Nelly, and its allowed values start with 1, 2, 3, 4 onward. 0 is not allowed. The principal quantum number is most closely associated with something like the zip code or the state that we're in. It is inherently a large description. It is not specific in and of itself, but it at least gives us a starting point. Its physical meaning is that it describes the energy level or location of the orbital, where a larger N means higher energy and farther from the nucleus. So the principal quantum number, the principal quantum number just refers to the location of the shells and how far away we are from the nucleus. So if I were just to draw a fictitious nucleus right here, a circle, and I were to draw those planetary rings around it, what I'm saying is that the electrons reside on those shells like so, floating around the nucleus. We've described it as orbiting the nucleus. The shell, the number, is what we're looking for the principal quantum number. The nucleus is assigned 0. That's why we can't use it for anything else. The first shell is n equal 1. The second shell is n equal 2. And the third shell is n equal 3. The fourth shell, 4. Fifth shell, 5, and so forth. So just like the zip code or the state, it gives us a starting point for where an electron can be located. Instead of just scrounging serendipitously wherever you want, we can narrow our focus to the first, second, third, or fourth shell. After the principal quantum number, we encounter what's known as the azimuthal quantum number. It is given the symbol L. The allowed values for L is n minus 1. Meaning, if, for example, n is equal to 3, L is equal to 2. If n is equal to 2, L is equal to 1. This is one of the big reasons why we will never have n equal to 0, simply because there can be no such thing as L is equal to negative 1. Negative has no physical meaning here. The physical meaning of the azimuthal number is that it describes the shape of the orbital. We've likened the concept of an orbital to that of a house where electrons live. Just like there is a variety of houses, townhome, condo, single story, multi-story, garage, all that stuff, there is variety of orbitals. When L is equal to 0, this is an s orbital. An s orbital is almost perfectly spherical. That's where the S comes from. So we liken it to that of a straightforward circle. So the house, the s orbital, is simply a circle, a sphere. When L is equal to 1, this is what's known as a p orbital. A p orbital resembles the infinity symbol shown here. You can also think of it as the number 8. You can also think of it as a dumbbell. I like to just call it an infinity symbol. This is a p orbital. L equal 2 is what's known as a d orbital. I'm going to need some space for this. Let me just shrink the others. A d orbital can be thought of as a 4-leaf clover. A d orbital can be thought of as a combination of 2 p orbitals. It looks like a 4-leaf clover. So it's sometimes referred to as flower petal shaped. Then we have L equal 3, which is described as an F orbital. Now, fair warning about the F orbital, that drawing is too complicated for Chem 300. So you are not expected to know what the shape is, to know what it looks like, to be able to identify it. All you need to know is that it exists, but that its drawing, its shape is very complicated. Think of it this way. If a d orbital is a combination of p orbitals, then an f orbital is a combination of multiple d's. So it gets really, really complicated really, really quickly. So that's something you'd encounter in an advanced chem course. Those are the first two. The next quantum number we're looking at, someone pick a color, not blue. Red. Did I use red already? I kind of already used red. Pick another color. Purple. Okay. Next one is magnetic. The symbol for the magnetic quantum number is M sub L. So that L is subscript. And its allowed values isn't a specific number. It's actually a range. It's from negative L to positive L. What's the physical meaning of this? It describes the number of orbitals present. Let's take a look at what that could mean. Well, we know that for L equals 0, we know from the previous page that this is an s orbital. This is what tells us that its ML is from negative 0 to positive 0. And well, frankly, that's just 0. Now, I want to be clear on something. I'm not saying there are 0 orbitals present. I'm saying that the amount is just 1, a sphere. Can't have a sphere in multiple different directions or orientations. That part might just not click just yet, but maybe it'll click once I describe to you L equal 1, which we know is a p orbital. Its range is negative 1, 0, and positive 1. The allowed values are from negative L to positive L. It's a range. What this tells us is that there are in total 3 p orbitals present. One could be vertical, as I just drawn on the previous page. One will be horizontal, and the other will be diagonal. You cannot say that each one of these links to another, meaning negative 1 can be any of them, 0 can be any of them. It does not relate to a specific one. The idea here is there are 3 values, so there are 3 orbitals. For L equal 2, that's of course a d orbital. That ranges from negative 2, negative 1, 0, plus 1, plus 2. Messed up on space. Let me just make some space for myself. Plus 1, plus 2. So based on this, how many d orbitals exist? 5. You do not need to know the complicated shape of every single d orbital. All you need to know about d orbitals is that they look like this 4-lobed clover, 4-leaved clover. And then, of course, finally, we have L equal 3, which is an F orbital. So no one's surprised. This is from -3, -2, -1, 0, +1, +2, +3. If we're keeping track, that's in total 1, 2, 3, 4, 5, 6, 7 F orbitals. So all of this has really just been describing the house and what's in the house itself. If we're saying that an electron lives in the s orbital, we're really saying there's only one room available. If we're saying that an electron lives in a p orbital, we're saying that 3 rooms are available. For D, we're saying there are 5 rooms, and for F, we're saying there are 7 rooms. All of this to say, multiple electrons will live in the same house. All right, we've already used purple, red, and green. Pick another color, not blue. I heard yellow. I feel like this yellow over here might be a bit too bright to pop up. Let's see. Orange. Oh yeah, the yellow is definitely too bright. Let's do orange. I like orange. Okay. The last the quantum number is the spin quantum number. Does that pop up well? Yeah, it pops up just fine. Yeah, I think it's fine. The spin quantum number is given the symbol m sub s. So that s is a subscript letter. And the spin number, its allowed values, is actually either going to be positive half or negative half. Only 2 values are allowed, a positive half or a negative half. The spin number describes the direction of the electron. What exactly does this mean? Well, going back to this magnetic number, I did liken this magnetic number to rooms in a house. I told you that the s orbital only has 1 room, that the p orbital has 3 rooms, that the d orbital has 5, and that the f has 7 rooms. Now, here's the thing about rooms. You can have roommates. The idea here is that in every orbital, I'll write it down. In every orbital, 2 electrons can be held or can be housed. So each electron will have a roommate. Electrons are negatively charged. You put 2 like charges in proximity, what's going to happen? Do you think they're going to attract or repel one another? Repel. But guess what? They're stuck in that room. So they're going to repel in opposite directions. What we say is that 1 electron will spin up, 1 electron spins down. The up is designated as the positive half, and the down is designated the negative half. There's nothing wrong with spinning up or down. It's just a fact of the matter. One of them will spin up, one of them will spin down. Here's the implication of this. In the s orbital, where there is only 1 orbital, 1 room, only 2 electrons can fit. In the p orbital, there are 3 in total. We saw them earlier, vertical, diagonal, and horizontal. If each orbital can hold 2 electrons, then 3 will hold 6 in total. Keeping it going, for the d orbital, of which there are 5, I trust someone to do the math. How many electrons can fit in total in a d orbital? 10. And then, of course, finally for the F, there are in total 7 orbitals, which will fit up to 14 electrons. So I want you to notice that we've gotten more specific in the location. Just like when we talk about an address, we start from something wide, like a zip code or a state. We start with something wide, like what shell are they on? As we get more specific, maybe the city or the street, we get more specific. What type of house do they live in? Within that house, how many rooms do they have? Within those rooms, who lives there? So when we think about electronic structure of atoms, I literally want you to think of it as this is the street address, the room address of that particular electron. Now, just as how there are rules when designing addresses, for example, every building must have a street number, and every building must be in a zip code for the county. There are rules to addresses. There are rules to quantum numbers. Number one, probably the most important, is known as the Aufbau principle. Created by a German named Aufbau. The Aufbau principle states electrons fill low energy orbitals first. What does that mean within the context of our analogy? It means that we'd rather fill rooms on the first floor first, then the second floor, then the third floor, and so forth. But then the question comes, how do we know what's a low energy orbital? Please take a second to either take a picture of this diagram or draw it yourself. This diagram is what shows us the rules on how to fill electrons. It's something that I do expect you to know, to memorize, to commit to memory. You can take a picture right now, or when the recording is posted later, you can, of course, just take a screen grab. I want to teach you how to read this diagram. You can see a couple things. You'll see number one, there's S's, there's P's, and there's D's and F's. There are also numbers in front of them. The way that we order or fill electrons is following the arrow. What this tells us is we fill 1s first, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, and so forth. So this diagram tells you the order that you need to fill these orbitals in. So there is no guesswork really needed of you, just a matter of do you remember this diagram or not? The really, really important one I want to point out here is, yes, of course, it makes sense. Oh, yeah, of course, we're going to fill up the 1s, then the 2. After the 2 comes 2p, and then 2 comes 3. So it goes in order, 1, 2, 3. That makes logistical sense. But around here at the 3p, after 3p, we fill 4s. And then we go back to 3. That's weird. That's unique. So I want you to absolutely note that we fill the 4s is filled before the 3D. So please pay attention to the arrows. It's a pretty easy graphic to draw and commit to memory. You're just writing stuff out: 1S, 2S, 2P, 3S, 3P, 4S, 4P, 4D. You just draw the arrows connecting them, and that's pretty much it. Number 2, Hund's rule. Hund's rule states that when filling orbitals of similar energy, electrons prefer to singly occupy before doubling up. This should make sense in principle. Everyone would want a room for themselves before being forced to have a roommate. Another way I like to think about this is if I get on the bus, some sort of bus transportation, I prefer to sit in my own seat where there's no one beside me. So I look for a seat where, it's completely free. I can just stretch right out. I'm a tall guy. But of course, if every seat already has someone, then I got to double down. It's the same idea here. Electrons would prefer to room by themselves. And only when all rooms are occupied will they say, okay, fine, I'll room you up. Number 3, Pauli's exclusion principle. Pauli's exclusion principle is a little straightforward. It just simply states that no 2 electrons will have identical quantum numbers or identical electronic structure. These are the big 3 rules that we will use when determining and answering the electronic structure for atoms. This is a lot of new content that is probably not familiar to most of you. Last class, we talked about naming. Maybe some of you are already a little used to something like sodium chloride, mercury, all that stuff. So this is some new content. So I want to be absolutely clear on something. Tomorrow's lab is the workshop focused on this topic. We're going to go over practice questions today, now, but the time for getting real practice in on this topic is tomorrow. All right? Let's do a couple questions. Let's see what kind of questions I would ask, what your answers should look like, and how you should think about it. The question says, provide the complete electronic configuration for the atoms below. And guess what? We're going to have that little Aufbau principle diagram at the ready, because we're going to refer to it. Let's start with a very, very simple one. Hydrogen. Hopefully we all have our periodic tables. If you don't, you'll need to refer to the one on the wall to the left. Hydrogen has only 1 electron. Its atomic number is 1. So if I were to ask you what's the address of this electron, of this atom, we follow the diagram. The first thing is we have to fill the 1s orbital. 1s. That's the first room filled. How many electrons are present? Just one. So it's simply 1s, 1. Within this simple designation, we know that the hydrogen's electron is on the first shell. It's in an s orbital, and there's only one electron in the room. What about something like lithium? Lithium is atomic number 3, so it has 3 electrons. So we're going to go fill in order. Starting off with the 1s. We know, I'll go back to it so you can see it. We know that the s has only one orbital, so it can fit 2 electrons. So this becomes 1s2. We're not done yet. We've only explained the first 2 electrons. We need the third. After the 1s, we fill the 2s. This becomes 2s1. Let's take one slightly more complicated. Let's do sodium, which is atomic number 11. So 11 electrons we have to consider. We're going to have to count, and we're going to have to go in order. All right, 1s first, 1s2, then the 2s, 2s2. After the 2s comes 2p. How many electrons can the p hold? 5? 6. 2p6. How many electrons have we explained so far? 2 plus 2 plus 6 is 10. So we still have one remaining. After the 2p tells us it is 3s. This is simply 3s1. Let's go a step further. Let's do a transition metal. I would like to do vanadium, which is atomic number 23. "23 electrons we have to account for. We're going to count in order, and we're going to remember our numbers. 1s2, 2s2, 2p6, 3s2, 3p6. Remember, where am I getting these numbers from? I'm just following this chart right here. I know that after 3s comes 3p. Let's check how many electrons we've explained so far. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. So we have explained 18 electrons. How many do we have left? We have 5 left. After the 3p is what? 4s. 4s2. All right, now we should be a total of 20 electrons. After the 4s is 3d. The remaining 3 electrons will go in the 3d shell. Do we have any questions so far? I see a hand in the front. Okay, so we know from our discussion about spin numbers that in every orbital, only 2 electrons can be held. We know that in the s, there is only one orbital available, so s can only hold 2 electrons. Similarly, for p, we saw up here it has a vertical, a horizontal, and a diagonal. Each one of them can hold 2 electrons. So in total, a p can hold 6. With the same logic, d can hold 10, f can hold 14. I see a hand right here. Very good point. He has raised a very good point. Just because they can hold up to 2, 6, or 10 doesn't mean they always will. It just depends on the number of electrons. Take, for example, hydrogen. Yes, you could go up to 1s2, but hydrogen only has 1 electron. You only need 1. Very good. You can say that same logic to something like vanadium. Everything here is filled except for the D. Remember that D has 5 orbitals, so it can hold 10 electrons. But we didn't need 10. We only needed 3. But they can go up to 10. Any other questions? See one over here on the left. We're going to draw in a bit. I'll come back to that question when we get there. Please remind me if I forget. Okay. Now, as you can imagine, the periodic table goes up to almost over 100 electrons. I think the highest number is 118. So that can be very, very daunting to have to write out the entire thing all the way to 7p over and over and over again. So something I've taught you, something I told you very early on was the laziness of chemists. That laziness also applies here. They coined something known as the noble gas configuration. The noble gas configuration is ultimately an abbreviated electronic structure configuration. It's a shorter. The idea is simple. Take, for example, a noble gas like neon. Neon is atomic number 10, and its complete electron configuration is 1s2, 2s2, 2p6. 2 plus 2 plus 6 equal 10. That's how we know we're on the right track. And we just did sodium earlier. We just saw that answer up here. Somewhere along the way, chemists realized, hey, isn't this the same configuration, or at least the same bit of it? Yes. So what they realized is, well, you can write the complete electronic configuration. You can also abbreviate it by substituting the configuration that resembles a noble gas and writing the rest of it as so. Again, the idea is something like sodium shares a bit of its configuration with a noble gas, so we can just abbreviate it saying, starting with the noble gas, and this is what's left. So the trick is identifying the closest noble gas and abbreviating the elements that come after. Take, for example, argon, which is atomic number 18. And we're going to again do vanadium 23. Now, we've already answered vanadium. I'm just going to copy that answer right down here. And we can see on the periodic table, argon is pretty darn close to vanadium. So we can make the argument, let's abbreviate it. Let's say 2 plus 2 plus 6 is 10. 10 plus 2 is 12. 10 plus 6 is 18. So this bit right here resembles argon's configuration. Exactly. 1s2, 2s2, 2p6, 3s2, 3p6. So all we really need to do after recognizing that is just abbreviate. Meaning all that's left is the 4s2 3d3. These are the two types of questions I'm going to ask you about this. Either provide the complete configuration, which requires you to write everything out, or I will ask you for the noble gas configuration, which just says abbreviate it. As with everything in life, there are exceptions. The exceptions to the electronic structure only apply to the 4s and 3d orbital. This is the only one that you need to know. The exceptions are as followed, or rather the one exception. A half-filled orbital is more stable than a partially filled orbital. Of course, fully filled orbitals are the most stable. What exactly does this mean, that half filled is more stable than partially filled? Well, think about the d orbital, for instance. We know that the d orbital can hold up to 10 electrons. This fully filled orbital is the most stable when all 10 electrons are there. This is more stable than the half filled, and half of 10 is 5. So D5 is stable, just not as stable as D10. And both of these are much, much, much more stable than literally anything else. D1, D2, D3, D4, D6, D7, D8, D9. Here is the implication of this. Let's look at an element such as chromium, which is atomic number 24. Let's do the noble gas configuration. Chromium is closest to argon. Argon is the first 18 electrons. So what we expect afterwards is 4s2, 3d4. Remember that of the 24 electrons, we can say that the first 18 resemble that of argon. And after that 18 is the remaining 6. This is what we expect. However, something magical happens. This 3d4 says to itself, man, oh man, I am just one electron away from being somewhat stable. All I need is a D5. Oh me, oh my, oh Romeo, where art thou? Where can I find you? Romeo, it's me, your sweet Juliet. I have an electron for you. The 4s will kick one of its electrons off and give it to the d orbital. This is what actually happens. Why? Because the D5 is much, much more stable than the D4, that it's willing to beg for it. Now, you may be wondering, but Sapreet, you just told us that fully filled is really stable. Why would the S want to give up on his electron? Isn't the 4s1 half filled? So yeah, the 4s1 may not be as stable, but it's like, you know what? That d orbital over there, that's really begging for it. I'm okay with a little bit of compromise. I like to use smiley faces. If the fully filled has two smiley faces and the partially filled is unhappy, then we can say the half filled are both smileys. This very rudimentary illustration makes it clear to us that the bottom one is more stable. It's happier overall. So this is something you have to keep an eye out for. You have to be able to recognize, oh my God, I'm just one electron away. Boom. This also happens with another one, copper, which is atomic number 29. Using the noble gas configuration starting with argon, what we expect is 4s2 3d9. This is what we expect. The first 18 electrons resemble that of argon, and the remaining 11 are here. But guess what happens again? That 3d9 says, dear God, Juliet, I just need one more electron. One more, and I'm unbelievably happy. The S gives it up. S says, fine, take it. I'm okay with it without it. And yet again, we can say, this guy may be super happy, this one is unhappy, but guess what? This one down here is much happier overall. Like I said, this is something that I do expect you to keep an eye out for, because I will ask you on the exam, please provide the electronic configuration for the following elements. And when this kind of thing happens, you are expected to recognize it and correct it. Do we have any questions? I see a hand over there to the left. I saw your second. Yes. The actual is what I would expect as the correct answer. Correct. Yes. The actual is the correct answer. You got a question? Yeah, of course. Correct. Yeah. I see a hand over here in the second row. Yes. You. Okay. I think I saw. Correct. It would be great if we had 10. 10 is fully filled. 5 is half filled. It's just happy. It's not as happy, but it's happy. And all of that is happier than 1, 2, 3, 4, 6, 7, 8, 9. Ion formation. So of course, when dealing with atoms and electrons, we of course have to remember that we can form a cation or an anion. How do we deal with that when it comes to the electron configuration? Well, it's actually fairly simple. Take, for example, a cation. Let's use sodium. Sodium is normally 1s2, 2s2, 2p6, 3s1. If we were to remove an electron, we would remove the 3s first. Why? Because it's the farthest out. Why? It's the highest energy. Remember, we talked about how that nucleus is around the rings. We've talked about how that valence shell, that outermost shell, is our first line of defense. So if we're going to remove anything, we're going to remove from the valence shell first. So Na plus is simply 1s2, 2s2, 2p6. You just remove it. And well, there was only one electron, so it gets deleted. What about something like an anion, which of course gains electrons? Something like chlorine. Chlorine is normally 1s2, 2s2, 2p6, 3s2, 3p5. Does anyone want to take a guess which orbital we're going to add an electron to? The last one, 3p. So Cl minus becomes 1s2, 2s2, 2p6, 3s2, and then finally 3p6. Highlighting the area so you know exactly what's changed. The weird one comes in when you're dealing with transition metals. You see, we know from nomenclature that transition metals will form cations. They lose electrons. We know that. We can confidently say that. That's okay. So if we were dealing with something like iron, iron is atomic number 26. Using the noble gas configuration, the first 18 resemble argon. Then we have 4s2, 3d6. So again, the first 18 electrons are here in the noble gas abbreviation, and the remaining 8 are located in the 4s2 and the 3d6. If I were to lose 2 electrons, I am here today to tell you that you would lose the s electrons first. This is not something you would have been able to predict otherwise. So I'm here today to tell you that transition metals always lose s electrons first. Of course, we can keep going. I can ask you what is Fe3 plus. So this is losing another electron. Well, there is no S to take from, so we just take from the D. 3d5. Yes, there is, but remember we've talked about how those valence, those outermost shells are our first line of defense. So if anyone's going to get lost, it's those guys on the very first infantry, the very outermost ring. So yes, there are S inside, but they're so far deep in, they're not going to lose at they're not going to be the first ones to be lost. Transition metals will always have the 4s first, right? So the transition metals I would ask you would only lose from the 4s. Maybe I'm not understanding your question, so maybe we can talk after class about it to get a little bit more clarity. Any other questions on this? Okay, I see two hands in the front. I thought I saw the one on the right first. Correct. Meaning, if you were to tell me on the exam Fe3 plus is AR 4s2 3d3, meaning you've only lost 3 from the D, that is wrong. Okay, I saw the person on the left. Yes, because remember that we know p orbitals can fit up to 6. Right now it only has 5. So if an extra electron is coming in, there is a room available. All of the others are fully filled, so they can't move in there. I see another hand in the second row. Good question. Transition metals will never become anions. Transition metals are always cations. They will always lose. Yeah.
For Cl, sleep minus 2.
Good question. Let's actually try it right now. So this student is asking, what if we had Cl2 minus? Now, obviously, the P is fully filled. So what comes after 3P? Look at that chart. Look at Aufbau. What comes after 3P? 4S. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. I see a hand in the front. Let's get to you in a second. Does that answer your question? All right, your turn. Yes, if we were to, for example, now go even further. So now it's 3 plus. If you want to lose an additional 5, so 8 plus, I'm not saying that 8 plus is possible, but if it were, then yes, it would just be the AR configuration. Yes. So that always comes back to this diagram right here. We get to transition metals once we hit 4s. After 4s, we fill 3d. After 3d, we fill 4p. And after 4p, we fill 5s. So it gets really complicated after we started choosing transition metals, which is why this diagram is so useful for us. When you say S rule, what do you mean by that? Yes. Yeah. Good questions. Okay. In the time that we have left, the question is draw orbital diagrams. For the atoms below. I think it was a student over here on the left that asked about what is that singly occupying. It was you, right? This is where it's going to come into play. All right. Here's a question. Let's draw the orbital diagram for sodium. We've done sodium a couple times by now. Sodium is 1s2, 2s2, 2p6, 3s1. Here's how the diagram looks. We're going to have an axis, an X and Y axis, where the Y axis represents energy. The X axis has no label. It's just there to help us organize our thoughts. It goes 1s, 2s, 2p, 3s, 3p, 4s, 3d. Please notice a couple things here. As best of my ability, I have kept all of the s's in their own category. As best as I can, I've kept all of the p's in their own sort of vertical area. And the d is all the way over here. You are not expected to memorize these drawings. I would like to show you what it will look like on your exam. Just so you understand that you don't need to memorize those drawings, but you do need to know to fill them in. Where is it? Where is it? Where is it? I'll show you what tomorrow's lab workshop looks like so you understand. I will give you the boxes. I want to be absolutely clear on this. You will not be needing to draw the boxes yourself. You will be given the boxes to fill in. Here's an idea. Let me just take a screenshot so I can just keep coming back to it. Oh, no. Again? You know what? I'll just save this and I'll crop it on GoodNotes. All right. Now we're going to fill it in. We're going to talk about that singly occupied business. First things first, why do I have 3 lines over 2p? Because there's 3 orbitals. For the same logic, I have 5 lines over the d. There are 5 orbitals. All right, what do we know? We know that there is 1s2. We know that one will point up, one will point down. They're roommates. They're electrons. They will spin up. One will spin down. In the 1s2, one up, one down. All right, that student had asked about what does singly occupied mean. Here's a really good example for the 2p. You enter a bus. You'd rather get in your own bench first. You fill them up one by one before you start doubling up. Meaning, notice that order. I did 1, 2, 3, 1 in each orbital first. Because if you had done it differently, 1, 2, 3, 4, this would be wrong. Does that make sense? Great. 2p6. What comes after 2p6 is 3s1. I have arbitrarily chosen to represent it as sticking up. Since there's only one, it could have either pointed up or pointed down. There is no more 4s, there is no more 3p, there is no 3d. This right here is the orbital diagram for sodium. Now, to the student's question that asked about that singly occupied business, in this question, I, of course, would not know on an exam what order you did it in, because these will be fully filled out. Whether you did this one at a time, then double up, or if you double it up from the beginning, I would not know the order that you took because the answer is correct. So let's do a question where it does matter. Let's do chromium. Yeah.
So what's the one up and then one's going down? Is there any difference?
Yes. So that comes back to the spin number. If 2 electrons live in a room and both of them are negative, they will repel. One will spin up, one will spin down. Traditionally, we say the spinning up is positive a half. Traditionally, we say the downward is negative a half. But if there are 2 electrons in a room, one will spin up, one will spin down. Cool. All right, now I'd like, is there another question? Yeah, that's fine. That is your choice. In this diagram, I had arbitrarily chosen that 3s to be pointing up. You could have written it pointing down and it would still be correct. But if there are two electrons together, one must point up, one must point down. You cannot have them both pointing up or them both pointing down. It could be either if it's by itself. Okay, let's talk after class about this because I'd like to finish with the transition metal. Okay. All right, for the transition metal, I'm going to use that diagram that you will be used to or see starting tomorrow. Like I said, I do not expect you to know to draw these diagrams. I will provide you with the boxes. So take a second for yourself just to redraw it as best as you can right now. All right, remember we've already done the electron configuration for chromium. We know the actual one, it's the first 18, then the remaining 6. Let's fill in the first 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we filled in the first 18 electrons. That's from the argon. That's a noble gas configuration for argon. All that's left, of course, is the 4s1 3d5. This is a good point for Aletha's question earlier. 4s1 tells us there will be one electron. I'm going to choose it drawing it down. All right. After the 4s1, we have the 3d5. Now, this really goes into that singly occupied because here's what the answer is. 1, 2, 3, 4, 5. Notice that I'm arbitrarily randomizing the direction of the electrons to show that it doesn't matter. Notice that each of the 5 electrons has its own shell, its own orbital. If you forgot that singly occupied rule, you would say 1, 2, 3, 4, 5. This would be wrong. So this is where that particular rule really comes into play, because I would recognize you didn't remember this rule at all if you wrote it like this. So it goes 1, 2, 3, 4, 5. Again, just randomizing the direction of the electrons to show that it doesn't matter. All right, this was a lot of new content. I understand completely if, it's still new to us all. We'll get some practice tomorrow during lab. We'll end the lecture for today. I'll print tomorrow's worksheet for you. So just come with your pen, pencil, and maybe a calculator. Remember that it's a dry lab, so I'm flexible on attire, but no food or drink. If you have any questions, you can come talk to me now. Have a good day. See you guys tomorrow.